So far you must have seen all my solutions are always simple, easy to understand and short, and keeping this trend in this question also. In this question it is given that for any 3 by 3 matrix M, let M bar denote the determinant of M. Let matrix E is this, matrix P is this, and matrix F is this. If Q is a non-singular matrix of order 3 by 3, then which of the following statements is true? You have to find the correct choice. For doing this question, you have to take care of one concept. See this matrix. This matrix contains 3 1 and 6 zeros, and all the ones are in different row and different column. And such a matrix can be easily seen to be obtained by applying some row transformation on a identity matrix. It is clear to see that if you use the operation of R2 changes to R3, by using this operation on this matrix, we will get this matrix. And we can also say that this matrix is obtained by applying the transformation C2 changes to C3. By using this operation, we can easily see that we have got this matrix from this matrix. And what is the use of this concept? Now I will tell you. The use of this concept is, if you multiply such a matrix with any matrix, say with that is, I have pre-multiplication of matrix P with this matrix. It is not necessary to find the product in normal way. You should note that and remember this thing, that when you will pre-multiply this matrix with this matrix, the matrix obtained in answer also operated by the transformation this, that is, the product will be A, B, C, because this matrix has been obtained by applying the transformation this on the identity matrix. Similarly, if I post multiply by such matrix, the matrix obtained in answer will also have been operated by this column transformation, because I can also say that this has been obtained by operating this operation on the identity matrix this. And it is not difficult to see also, if you multiply these two, keeping this concept in mind, it is also very easy to note that P square will be surely identity matrix, because square of such matrix is always identity matrix. The reason being, P square means P into P. I can say that I have pre-multiplied P by P, and Pre-multiplication by P means doing the transformation of this on the matrix P. That is, in other words, P square will be obtained by using this operation on identity matrix two times. And it is obvious that if we use this operation on this matrix twice, obviously we will get the same matrix back. Hence, square of such a matrix is also always identity matrix. Note these things, and I'm going to use these concepts in the question. For checking the choice A, first I have to find the value of PEP. PEP means PE into P. We can also say P into EP. That is also correct because associative property is satisfied by matrices. And to find PE, it is not necessary to find PE by proper multiplication of P and E. We can say, as just now I told you, PE means applying the transformation of R2 changes to R3 in the matrix E, because here I have pre-multiplied P by E. If I want to find EP, in that case, I will get the result of operating the operation this on this matrix, as just now I told you. Hence, directly I can say PE, that is 8, 13, 18, and result will be 1, 2, 3, 8, 13, 18, 2, 3, 4. This is the value of PE. And again, now PE, P means post multiplying matrix P with this matrix. That is obviously the result will be obtained by doing the operation of this on this matrix. That is, I will get 3, clearly this is the matrix F from here, you can see. Hence I can say this part is true, and this thing I just now told is also true. Now the next is, because we are dealing with multiple answer questions, hence other choices will also required to be checked. For choice B, left hand side is EQ plus PF Q inverse equal to EQ plus P into Q inverse, putting the value of matrix P. And according to associative property, any two matrices can be multiplied first. Hence, First I multiply P and P, that is P square, and P square is clearly I, hence I get EQ plus EP Q inverse, that is Q plus PQ inverse, that is determinant of E into determinant of Q plus PQ inverse. Determinant of E is clearly 0 because it is easy to see 1, 2, 3, 2, 3, 4, 8, 13, 18. All these three numbers are in AP. Hence, obviously, if I use the operation C2 changes to C2 minus C1 and C3 changes to C3 minus C2 on the corresponding determinant, I will get the answer as 1, 2, 8, 1, 1, 5 and 1, 1, 5 again, and hence the answer will be 0. Therefore, determinant of E is clearly 0. Hence, I get the answer 0. Now, let us calculate the right hand side. This clearly means determinant of E into determinant of Q, and because this is 0, the whole becomes 0. Therefore, the answer of this is 0. Now, let us calculate this. From here, it is clear that determinant of F will be determinant of P into determinant of E into determinant of P, that is determinant of E 0, therefore determinant of F will also be 0, and the value of this becomes determinant of P into determinant of F into determinant of Q inverse, and because this being 0, the whole becomes 0. Therefore, the value of this also becomes 0. Therefore, both are equal. Hence, A and B both are correct choices. Now you have to check the choice C. Obviously, this is wrong because determinant of E being 0, left hand side and right hand side both becomes 0, and 0 greater than 0 is wrong. Therefore, C is wrong choice. Last is to find the sum of the diagonal elements of P inverse EP and plus F. Just now I showed that P square is I. This means I can say P inverse is equal to P. Hence, this becomes PEP and PEP is F. Therefore, this becomes 2F. And further, this is E plus PFP because P inverse is P. And putting the value of F, this is also I, this is also I, therefore it becomes E plus E, that is 2E. That is, this becomes 2E and this becomes 2F. Now we'll calculate the sum of the diagonal elements of 2F and 2E. Obviously, sum of the diagonal elements of 2E will be 2 into 1 plus 3 plus 18, that is 44, and sum of the diagonal elements of 2F will also be 2 into 1 plus 18 plus 3, that is again 44. Hence, D is also correct choice.